Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome back to lecture number 26, part 1 on the topic cold storage design for negative temperature application. In the previous lecture number 25, both part 1 and part 2, designed cold storage for a blast type of freezer, and in the second numerical question, design was carried out for a plate type of freezer. Now, in this lecture, we are going to design a cold storage for a negative temperature application, especially for storing meat. The product used is meat. So the room dimensions are given, length, width, height. Ambient condition is given, 40-degree dry bulb temperature. Product initial temperature is given. Product initial temperature is given. Product final temperature is also given. So let me write the given data. So this problem also, this design also will be carried out in two parts, part 1 and part 2. Given data. Dimensions are given. (10 by 13 by 7). 10 meter by 13 meter by 7 meter. That is, length is equal to 10 meter, width is equal to 13 meter, height is equal to 7 meter. Product initial temperature is given, that is T1, 18 degrees centigrade, that is 18 degrees centigrade. Loading temperature is given, that is T2. Freezing temperature is TF, and final temperature is T4. T3, 18 degrees centigrade. Loading temperature is T2. This is initial temperature. Loading temperature is given as 4 degrees centigrade. Product loading temperature is 4 degrees centigrade. Loading temperature. That means from 18 to 4 degrees centigrade, it is pre-cooling is done. Lower from the initial temperature, from the ambient condition, from initial temperature, not ambient condition. Ambient condition may be more than this one. From the initial temperature of 18 till a temperature of 4 degree, it is pre-cooling. Then from after pre-cooling up to freezing point, we will have the sensible heat above freezing, then latent heat during freezing, then the heat load due to sensible heat below freezing will come. TF is equal to minus 2.2 degrees centigrade, freezing point. Freezing point or freezing temperature. Let us write freezing temperature. And T3 is also given. Freezing temperature is minus 1.7. Product final temperature is minus 20. This is not 2.2. This is minus 20. Final temperature. Let us write the other data. Specific heat, two specific heats are given. One is above freezing, one is below freezing. Specific heat above freezing is 2.48, and specific heat below freezing is 1.91, 2.48 and 1.91. 2.48 kilojoule per kg Kelvin, 1.91 kilojoule per kg Kelvin. So this is above freezing, this is below freezing. Insulation, let us write the thickness value. Insulation given is polyurethane board, that is puff. Thickness of insulation is 200 millimeter. Polyurethane board or foam, that is puff. Thickness of insulation is 200 millimeter, which is equal to 0.2 meter. Latent heat is given. Latent heat of freezing is 194 kilojoule per kg. There is one topographical error. I think two datas are repeated. Outside air enthalpy is given directly, and inside air enthalpy is also given. So here it is repeated. So let me delete it here. The repetition. So these two can be good because it is already there. So let me save it. And so let us calculate the transmission load. The other data as required. When I am substituting, I will be taking it. Let us calculate the transmission load, and the product is meat. Product to be stored is meat. First, let us calculate the transmission load. QT. As usual, the first step is to take the value of thermal conductivity from the table, from ISHRE cold storage design handbook, a guidebook. Table number 2.1 for polyurethane board. The value of K is equal to, so this is table number 2.1. These are all the values in SI unit. Polyurethane board, that is the first one. So this is the value which I will take. The range is given from 0.023 to 0.026. I will take this value, 0.023 watt per meter Kelvin. Once we know the K value, area, the dimensions of the room are given, thickness of the insulation is given, we can estimate the transmission load. Therefore, QT is equal to, the formula is U into A into delta T. U is K by X into A is A into delta T. A will be 2 into length into width plus width into height plus length into height into delta T. Let us substitute the value. K value we have taken from the table number 2.1, 0.023. 0.023. Thickness is 0.20 into, the dimensions are 10 by 13 by 7. Delta T is given. That is the difference between the outside temperature and the inside temperature. So this is the value which I have taken from the detailed solutions of all the design of all the numerical questions are given in the PowerPoint presentation. So to make the learners understand as I am explaining, so I am writing it again, so that step by step it will be easy for the learners to. So the temperature is, outside temperature is 40, and the inside temperature, the product has to be cooled up to -20. -20. So let me write that also in the given data. Outside temperature is equal to 40. Inside temperature, that is the cold room temperature, -20. So this is delta T. This is delta T. 40 minus of -20. When we calculate, we get the transmission load as 4 kilowatt. Next, let us calculate the product load. Q suffix P. In the product load, the initial temperature of the product is given. Loading temperature is given. Freezing temperature and below freezing. So 4 temperatures are given: T1, T2, T3 and Tf. So first I will calculate the sensible heat. Sensible heat above freezing, that is cooling the product from these two, T1 to T2. T1 to T2. From 18 degrees centigrade to 4 degree centigrade. This is like similar to the pre-cooling. So this is Q1 is equal to M into Cp into T1 minus T2. This Q1 term was 0 because this details was not given for the previous two numerical questions pertaining to negative temperature application that was solved in the lecture number 25, part 1 and part 2. Let me write the quantity of the product. Since the M value is required, it is given as 20 tons. So 20 into 1000 kg. M is equal to 20 tons. M is equal to 20 tons. That is equal to 20 into 1000 kg. So this is equal to 20 into 1000. Here the Cp value is above freezing only. Above freezing. So Cp value above freezing is 2.48. 2.48 into T1 is 18 to T2 is 4. So Q1 is equal to, you will get it in, that is per day, 6,94,400 kilojoules per day. 6,94,400 kilojoules per day, which is equal to 694,400 divided by 24 hours into 3,600. That will give in terms of kilowatts. So 6,94,400. Q1 comes to 8 kilowatt. 8 kilowatt. Next one is sensible heat above. This is also above freezing. Above freezing that is cooling from this temperature from 4 degrees centigrade to minus 1.7. From 4 degrees centigrade to minus 1.7 degree centigrade. So this is Q2 M into Cp into the temperature is T1 is 18, T2 is 4 and Tf is freezing point, that is minus 1.7. So the temperature is from T2 to Tf. T2 to Tf. Substituting the values, here also this is above freezing. The Cp value to be substituted with regard to the Cp value above freezing. This is, let us check the M value. M value is 20 tons, correct. 20 into 1000. Cp value above freezing is the same value which we have to take, 2.48. 2.48. T2, that is the storage temperature, 4 minus of minus 1.7, that is the freezing temperature. Q is equal to 2,82,720. 2,82,720 kilojoule per day. So this is equal to 2,82,720 divided by 24 hours into 3,600 seconds. So this is equal to, this is Q2. So Q2 is equal to 3.3 kilowatts. 3.3 kilowatts. I think here 24 is missing. So let me make small correction here. So this is 24 into 3,600. So Q2 value comes to 3.3 kilowatts. .3 kilowatts. Next one is latent heat. Latent heat Q3, that is equal to M into H of latent heat, that the enthalpy value, that is 20 into 1000. Latent heat value is given as 194 kilojoule per kg. So we will get 194. So that is, this M is in per day only. So that's why for all the quantities it is in kilojoules per day. So 38,80,000. 38,80,000 kilojoules per day. So divided by 24 into 3,600. So that will give in terms of kilowatts. Q3 value is 44.9 kilowatts. 44.9 kilowatts. Next, I will do the sensible heat below freezing on this side. Sensible heat below freezing. This is from cooling from freezing temperature minus 1.7 degrees centigrade to the required temperature of minus 20 degrees centigrade. So this is from, so this will be Q3, sorry Q4. Q4 is equal to M into Cp into Tf minus T3. T3, that is cooling from the freezing point till minus 20. That is the storage temperature. Here we have to substitute the value of Cp below freezing. below freezing. This value you have to substitute. 1.91 20 into 1000 into 1.91. So here Cp value is below freezing. Into Tf is minus 1.7 minus of minus 20. So we get Q4 as, see here I have substituted the value of the Cp value below freezing, 6,99,060. So that is in kilojoules per day. That is equal to 6,99,060 divided by 24 into 3,600. So that will give Q4 8.1 kilowatt. 8.1 kilowatt. Respiration load Q5 is equal to 0 since meat is not a live product. So therefore the total product load is product load QP is equal to Q1 plus Q2 plus Q, let me write it, letters or not, Q1 plus Q2 plus Q3 plus Q4 plus Q5. So this is equal to Q1 is 8 kilowatt, Q2 is this is Q2 3.3 kilowatt, Q3 is 44.9, Q4 is 8.1 and Q5 is 0. Total product load comes to, so this is the total product load. This is the total load. So total product load is Q1 plus Q2 plus Q3, Q4, Q5. It comes to 64.3 kilowatt. 64.3 kilowatt. So let me emphasize again here that compared to the lecture number 25 and 26, the design of cold storage for negative temperature application, in both the design which we have done in lecture number 25, the initial temperature was not there, so the pre-cooling part calculation was not considered. So we have calculated Q2, Q3, Q4. Of course, Q5 is 0 because the product considered dead one, not a live product. Whereas in lecture number 26, in this part 1 lecture, initial temperature, then we have got final temperature, freezing temperature, then there is a loading temperature is also there. 4 temperatures are given, T1, T2, TF and T3. From T1 to T2, it is, that is like pre-cooling. T2 to TF, it is sensible heat above freezing. Both Q1 and Q2 are above freezing, so we have to take the same value, the Cp value above freezing. And Q3 is latent heat. Q4 is sensible heat below freezing. Q5 is respiration load, which is equal to 0. So I will stop this lecture at this point. Thank you.